then strength, then stress versus strength comparison, that is theory of failure. Okay, right. Then we started this, right. Here we are going to discuss three informations. Out of the three, one is discussed yesterday. Right. Here, what is the outcome in this discussion? Even though many stress values are calculated within the single object. Who calculated? We have calculated. Right. Which stress should be compared with the strength? Right. Maximum value. Okay. For safer design, maximum calculated stress should be compared with the strength. Right. This is first point. Right. Next point. Second one is important one. See, note this. It is a stepped bar, right? It is 2 meter square cross section area. Okay, or we will keep it in mm square. Okay, it is a 100 mm square. Okay, 100 mm square cross section area. The second step, smaller one, is 50 mm square cross section area. 50 mm square cross section area. Okay, right. The applied load is 1000 Newton. Okay, right. Force is applied. It is a uniaxial bar. Uniaxial bar. Okay, right. Even though the rod looks like 3D, okay, we are considering the loading and the effect of the loads along only one direction, in this direction only. So it is assumed as one dimension. Okay, right. So we will discuss later. What do you mean by degrees of freedom? Number of degrees of freedom for 3D, 2D, 1D. Okay, what are the corresponding loads? What are the corresponding equilibrium equations? Everything you'll see. Okay, actually they are engineering mechanics informations. Anyway, I will give you, right? I will not leave you. I will give all the informations, basic information, right? Now, you have to answer me, right? What is a stress? I am your manager. I am asking you, what is a stress in this bar? Okay, tell me. Answer, please. You don't hesitate to answer, right? Most of you are preparing for TRB. You are all teachers, almost teachers. Okay, right. So main requirement is participation. Don't worry about your answer is correct or not. That is secondary one. Just participate. Okay, right. What is a stress?
1000 by 150.
Value. Other students, quick. Any answer, easily you can calculate.
6.7.
6 point. Okay. So stress is equal to 1000 by 100. One person is saying it is 10 megapascal. Another student is saying sigma is equal to 1000 by 50 is equal to 20 megapascal. Okay, right. So another student is saying 1000 by 150. Actually, we should not add these two areas. Compulsorily, we should not do that. Okay. Right. So I am not writing that information. Okay, no problem. Participation is important, right? Either you have to consider this cross-section area. Cross-section area means, very important point. Cross-section means perpendicular to the loading direction. Okay, right? Or this cross-section area. This is a simple tensile stress. So P by A. So P by this area or this area. Right. Now which is correct? Tell me. 10 megapascal or 20 megapascal?
Sir, do we take the critical one?
See, I am your manager. You have to tell me the final value only.
Then
You have
20,
enough experience.
Then 20.
20. Okay, right. So 20 is correct according to you. Okay, because yesterday we discussed that within a single member, we have different stress values. See, in this cross section 10 megapascal, in this cross section 20 megapascal. So which stress would be conveyed to the manager? 20, right? Why should we convey the maximum stress? Because my manager is going to compare the stress with the strength. So we know that maximum stress should be compared with the strength. That is why I have given maximum stress to my manager, right? So according to you, 20 is correct. According to you, right? But it is wrong. Okay, right? Whenever the sudden change in the cross section, is available in the material. Okay, right? Stress will be locally raised, amplified. Okay, so here area is suddenly reduced. Right? So in that sudden change in cross section zone, stress will be suddenly amplified, magnified. Okay, that concept is called as stress concentration. Stress concentration, very important concept. Okay, stress concentration. Okay, right? So where is the stress concentration zone? See here. See in that zone, stress will be more than 20 megapascal. Stress will be more than 20 megapascal. Okay, right? Sigma max is equal to sigma critical. Already you know, right? 20 is a critical value, right? Into KT or SCF, stress concentration factor. Right? Stress concentration factor will be always greater than 1. Always greater than 1. Greater than 1. Always. Okay. Sometimes 2, 2.5, 3, sometimes 27 also I have seen. Okay. Right. Depending upon the change, sudden change. Right. Okay. Right. Next question. Sir, whether stress concentration is developed only due to sudden change in geometry or any other reason is there, right? There are 3 type of reasons for stress concentration. Okay, 3 type of reasons: sudden change in material, sudden change in load, sudden change in geometry. Okay, so due to this, stress will be concentrated. Okay, right. Here, what is the critical stress? 20. Okay, this is wrong. This is sigma critical. Right. Actual sigma max is multiplied by SCF, right? So SCF, stress concentration factor, is represented by KT. KT. Okay, K suffix T. So I will give the information about stress concentration. Right. Stress concentration. See, important question, interview question. Right. So it is a localized stress amplification, not globalized, localized. Localized stress amplification due to first point, sudden change in geometry. Sudden change in geometry. Right. Second one, sudden change in material. So sudden change in material means, can I give some example? Right? For example, it is a steel. This is copper. This is copper. Right. So in that junction, stress will be amplified. Okay. Right. Then third reason is sudden change in load. Sudden change in load. Okay, right. So this can be used for two cases: sudden change in geometry as well as sudden change in material. Right. Sir, what do you mean by sudden change in load, sir? Right. See, it is a uniaxial bar. Uniaxial bar with a uniform cross section from left end to right end. Okay, right. Now tell me, what is the value of load acting in this point? What is the value of load acting in this point? In that particular particle. Say we are applying point load in this point. We are applying point load here, right? My question is, what is the load applied in this particle?
Nothing.
Nothing, zero, zero, zero. Okay, right. So what is the formula for stress? Load by area, right? Load by area, right? For example, this load is 1000 Newton. Cross section area is 100 mm square. What is the expected stress? 10. 10. Okay, right. See how the stress is varying. All of you see here. Okay, right. So in this point, stress is very high, right? In the nearer points, almost zero, right? So here it will be more than 100. It will be more than 100. Sorry, more than 10 megapascal, more than 10 megapascal, right? If you travel after some distance inside, right? Now I'm going to draw the stress pattern. Right. See, the peak is little bit reduced, right? So almost same magnitude at all the points. Right. Again, if you travel inside, the stress magnitude will be equal at all the points. Okay, right. So nearer to the point load application point, we cannot expected uniformly distributed stress. If you travel at least 2.5 times the diameter or width, 2.5 times the diameter or width, right? Inside the material, you can see the uniformly distributed stress throughout the cross section, right? Okay, right. So if you are watching nearer to the loading point load point, you can see the localized stress amplification. Localized stress amplification. What is the name of that? Stress concentration. Stress concentration. It will be more than the expected stress value. It means more than 10 megapascal. Okay. Right. Okay. Right. So now you can understand, right? maximum stress should be compared with the strength, first point, right? Then if there is sudden change in geometry, stress concentration will be developed, right? So we have to multiply the critical stress value with the stress concentration factor. Who will give the stress concentration factor? It will be given in the examination. Actually, we have to take it from the data book, but the data book is not permitted. So they will give the stress concentration factor in the given data, right? In the examination, right? So stress concentration is due to three reasons: sudden change in geometry, sudden change in material, sudden change in load, right? So the sudden change in load effect, right? It is called as Saint Venant principle. Saint Venant principle. What is a principle? If you travel more than 2.5 times the diameter or width of the cross section, the stress distribution will be uniform. Okay, right. Next, sir, here what we did already, we thought that we are clever. See, this is wrong, this is clever answer. But again we are studying one more information. The critical stress is multiplied by stress concentration factor, right? So it means the stress should be overestimated. Stress should be overestimated. Okay, right. That's why we told stress concentration factor is greater than 1, right? So overestimated stress. So we have to take overestimated stress for comparing with the strength, right? Next information, right? See, in the theory of failure, stress is compared with the strength, right? We have calculated the stress, right? The stress is 300 megapascal, right? Strength is 350 megapascal. The design is safe. Design is safe. The component will be safe. Right? Who gave this number? We have calculated. Who gave this number? It is available in the data book. It is available in the data book. Who gave this number to the data book people? From the testing laboratory. Where is the testing laboratory? It may be in the US, right? Or it may be in Germany, right? So they have tested the mild steel in the standard testing laboratory. They told that strength is 350 megapascal. So we are purchasing mild steel in a nearer sale, Steel Authority of India Limited. In Salem, one steel plant is there. Right? We are purchasing there. Right? Now the question to you, right? Can you give the guarantee that the steel purchased in Salem is compulsorily having the strength of 350 megapascal? Can you give the guarantee?
If it is certified by the association,
Yeah, there are a lot of reasons. Climate change, testing condition change, manufacturing condition change, lot of difference will be there because this data is taken from the US. Okay, ASTM testing laboratory. Now the question is, the steel purchased from Salem, Steel Authority of India Limited, our central government industry, right? The strength is 350 megapascal or it may be less than 350 megapascal. You have to give the idea. You have to think about safer side only.
it would be less.
It would be less. It would be less. It may be due to climate change. It may be due to manufacturing conditional changes. Okay, right. So in the data book, it is written as 350. Okay. Unfortunately, due to our bad time, the steel purchased from Steel Authority of India Limited Salem having 290 megapascal strength actually. Right. it means, see, according to data book information, you will say your design is safe, right? But if you use this geometry in the field, actual field service, right, the component will be failed, because the component is made of mild steel. The original strength of the mild steel, our mild steel is 290 megapascal. So stress, expected stress is 300 megapascal, right? So the component will fail, right? So what to do? So in the data book, original strength value will be available, original strength value, okay, right? For our safety purpose, we have to underestimate the strength. We have to underestimate the strength by some factors, right? For example, by 2, right? So it means, what is the new strength value? 175, right? Now, what will be your work on your stress calculation? You will try to maintain the stress value within 350 or within 175.
Within 175.
Within 175. Within 175. Okay, right. Within 175. Right. So theoretically, you are trying to maintain the stress within or below 175 megapascal, even though during the service, due to unexpected load, due to speed breakers or damage in the road, right? Due to unexpected heavy load, stress is increased from 175 to 200 megapascal. Unexpected rise. The component will be safe or fail. The component will be safe or fail. Safe, because you know that the 175 is not the original strength. Original strength is more than that. So already we have underestimated strength value. Okay, right. So even though small rise in stress may not lead to failure. Okay. So for the safety purpose, we are underestimating the strength. Right. The underestimating factor is nothing but factor of safety. Factor of safety. Right. Now tell me, which stress should be compared with the strength? Overestimated stress should be compared with the strength. Which strength? Underestimated strength. Okay. Stress should be overestimated, strength should be underestimated. If you do both, your design will be safe at any cost, at any bad situation. Your design will be safe. Right. Example for overestimation, stress overestimation is, example is sigma max equal to sigma critical into stress concentration factor. Okay. Underestimating the strength. Example is strength by original strength, right? Or permissible strength is equal to permissible or allowable strength is equal to original strength by factor of safety. What will be the factor of safety value? Greater than 1. What is the SCF value? That is also greater than 1. Okay. So don't forget, overestimated stress should be compared with the underestimated strength. Right. Next point. Very important information. Right. So focus only one diagram. This one. Right. It is a uniaxial bar. Uniaxial bar. Okay. Right. I am applying tensile stress. Tensile stress. It means it is a normal stress. Okay. Right. Tension, compression, both are coming under normal. Okay. Right. So the applied stress is normal stress. Example, our uniaxial tension test. We have conducted uniaxial tension test in our strength of material laboratory in our college. Right. In which material we have conducted uniaxial tension test? In which material we have conducted uniaxial tension test? Tell me. Answer.
Mild steel.
Mild steel. Mild steel. Very good. Mild steel. Okay. We have conducted uniaxial tension test in the mild steel. Mild steel is a ductile material. Ductile material. Okay. Right. Mild steel is a ductile material. In the ductile material, we have applied normal stress, tensile stress. Right. What type of failure you have observed in the uniaxial tension test? Shear failure or normal failure? Normal failure means material separation. For example, see, this is a material. Okay. Right. Initially, these molecules were in contact. Right. So after some time, they are separated. Separated means normal. Okay. So for example, I will give another example. Right. So after fracture, this molecule and this molecule both are separated from each other. It means it is normal failure. Normal failure. Right. Sometimes it will be like this. Initially, these molecules were in contact. After some time, they are sheared off. They are sheared off. Material slip. Material slip. Right. Here material open. Here material slip. Right. Slip means shear. Material open means normal stress or normal failure. Okay. Right. Now tell me, did you observe that in the uniaxial tension test? It was failed. Mild steel was failed by shear. Shear. Right. What is the name of that failure? Cup and cone fracture. Cup and cone fracture. Right. This is a shear failure. Shear failure. Original name is cup and cone fracture. Okay. Right. So applied load is normal. Applied load is normal. Normal load. Normal means it may be tension or compression. Here we are applying tension. Right. See, we have doubt. See, in the ductile material, in the mild steel, I have applied normal stress. The material failed was by shear. Shear. Right. But I did not apply the shear. What happens in between? Something happened in between. Okay. Right. So that we will discuss. Right. So at what angle you have observed this shear? Do you remember? At what angle you have observed the shear failure in the uniaxial tension test? It was at 45 degree. It was at 45 degree. Okay. Right. See, I am representing one molecule here. This molecule and this molecule. Right. See, if you bring this component, right, both will be touching like this. Both molecules. Right. If you remove in this direction or if you move in the right hand side, they will be separated. Right. By slip. Right. separated by slip phenomena. Right? This surface and this surface, both will be sheared off like this. Slip takes place. Right? So it was observed in our college laboratory. Okay, right. So first experiment, applied load is normal, failure is due to shear. We have doubt. Okay, so keep it as it is. Right. Next, in the same ductile material, right, same round rod, we are applying the torsion. So the torque is creating shear stress, torsional shear stress. Okay, right. Right. It is applied load, shear load. Applied load is shear. Where you are applying? On the external surface. Right. See, all the keywords are important. Right. So when we are applying the torsional shear load, right? What is happening? Right? Just assume, all of you, just assume that 1 rupee coins are stacked together. These are all 1 rupee coins. Right? With the help of pasting material, you are stacking 1 rupee coins. Right? What is the geometry you will get? If you stack 100 numbers of 1 rupee coins, one over another. Cylinder, right? So in the cylinder, you are applying the torque. One is in the right clockwise rotation. In the other end, it is counterclockwise rotation. So it is torsion. Right? If you apply the torque continuously, right, the shear between two adjacent coins will take place. Okay, right. So that is nothing but torsional shear. Right. So the failure is happening due to shear failure. Right. Right. See the left hand side, both are ductile materials. First we applied normal load, failure was shear. Second we applied torsional load, means shear load, failure was shear failure. Okay, right. So keep the information as it is. Now coming to brittle material. Brittle material. So you can take our whiteboard chalk piece. Okay, right. So I'm going to apply tensile load. You can do this experiment in home. 2 experiments in your home. Right. You are applying the tensile stress. Applied load is normal. Right. Applied load is normal load. Right. So what type of failure is observed in the chalk piece? Brittle material, flat surface. This flat surface, right? So the molecules are separated before failure. Both molecules are adjacent to each other. Okay, right. So after the failure, both are separated. Separated means which failure? Molecules are separated means normal failure or shear failure? Normal failure, right? Normal failure. Right. See, I have applied normal load. Failure is also due to normal stress, right? In the same chalk piece, right? Another new chalk piece. Again, I'm going to apply torsional shear load, twisting. Tau torsion. Torsional shear stress is applied. Okay, right. What type of failure observed? Right. See, before failure, these two molecules were adjacent to each other, right? After rotation, this is rotated in the clockwise direction, this is rotated in the counterclockwise rotation. Okay, right. The molecules are separated. The molecules are separated, right? So separated means normal failure. Normal failure. Molecules are separated during fracture. Normal failure. It means normal failure means what? Failure is due to normal stress. What type of load is applied? Shear load. See the slide, full slide. Now we are going to make 2-3 conclusions, right? We are applying the normal load in the external surface. Failure is due to shear stress. Failure is due to shear stress. It means something is happening inside the material. So what is happening? The externally applied normal stress is transformed into shear stress inside the material. Transformed. Okay. So external surface normal stress is converted into shear stress. See, if the angle, all of is here, at this surface, right? Watch carefully. See, in the external surface and internal surface, both are parallel. Right? 0 degree. Angle between these two lines is external surface and internal surface. Both are at 0 degree. Right? So no transformation occurs. At 0 degree, no transformation occurs. Very, very, very important information. Get question. Right? Suppose if I rotate by 1 degree, it is 1 degree. 1 degree. Right? The external normal stress, externally applied normal stress will be converted into normal and shear. Normal and shear. Right? Then I am rotating by 2 degree. Again, now internally transformed normal and shear will change in magnitude. Right? Again, rotation by 3 degree. Right? So internally transformed normal stress magnitude is changing, shear stress magnitude is changing. Right? So inside the material, normal stress magnitude, shear stress magnitude, both are changing continuously in the sinusoidal pattern. Don't forget. Right? So it means at one angle, at particular angle, internal shear stress is maximum. Internal shear stress is maximum. That internally developed shear stress, maximum shear stress is reaching the strength value of this material. That is why the material is failed by shear. Okay. Right. Next test. Here we have applied shear stress in the external surface. Okay. Right. This is the external surface. This is the failure surface. What is the angle between these two? Angle between these two. Internal failure surface. This is the external surface. Angle between these two. How much? 0 degree. 0 degree. 0 degree means transformation will occur or not. 0 degree means transformation will occur or not. No transformation. So it means at 0 degree inside the material, right? External stress is equal to internal stress. External stress is equal to internal stress. So here external stress is equal to internal stress, right? Right. Suppose if I calculate in this plane, again both normal and shear will be available. Normal and shear both will be available, right? These two are transformed due to externally applied shear, right? But at particular angle here in this angle, it means 0 degree, shear stress is maximum. Shear stress is maximum inside the material. That maximum internally calculated shear stress is equal to strength value. That is why the component is failed by shear. Okay, right. Now here normal load, normal failure, no problem, no doubt. Here you have doubt. Sir, I have applied shear load, but failure happens by normal stress. Right. So how it is possible, sir? How it is possible, sir? Right. See, the externally applied shear stress is transformed into normal and shear. Right. So at one angle, at particular angle, the internally transformed normal stress is maximum. Internally transformed normal stress is maximum. That internally transformed maximum normal stress is causing the normal failure. It means principal stress is causing the normal failure, right? See, I'm going to draw the stress pattern here. It is a gate question, TRB question also. Okay, so this side tension, this side compression. So this tension is dominating inside the material. It means at this angle, this tension is maximum. That maximum internally transformed normal stress, that is principal stress, is causing the failure. That stress is equal to normal strength, so the component is failed. Right. Now, I'm going to ask a few questions. Right. So already you know that externally applied stresses are transformed inside the material. Okay, right. Now, first question, where you are going to apply the stresses or loads, external surface or inside the material?
Externally.
External surface. In the external surface only we can apply practically, right? First question answer is correct. Second question, the failure is due to externally applied stress or internally transformed stress? Very
Internally
important question.
transformed.
Right. So failure is decided by internally transformed stresses. Okay, it's very important point. You will write the conclusion first. Failure is due to, first point. See, these things will not be available in the textbook. Note this carefully. Failure is or failure occurs due to internally transformed stresses. Right. So during the internal transformation, normal stresses and shear stresses will vary in the sinusoidal pattern. At one stage, normal stress will be maximum at particular angle of rotation inside the material. At particular another angle of rotation inside the material, shear stress will be maximum. Okay, right. Next question. Dangerous question, right? The type of failure means only two type of failure you have observed, right? Normal failure, shear failure. Normal failure means what? Internally transformed normal stress, that is principal stress, is equal to tensile strength. That is why molecular separation occurs. It is called as normal failure. Right. Then here, internally transformed maximum shear stress is equal to shear strength. That is why shear failure occurs. Okay, right. Now the question to you, right? Question to you. The type of failure, whether it is normal failure or shear failure, is based on material or applied load. Tell me. The type of failure depends upon the material or type of load. Material. Very good. Excellent answer. Material. So type of failure depends on the material. Okay. Right. Now tell me, what is the observation you are making? You told that type of failure, whether it is shear failure or normal failure, depends upon the type of material. Okay, right. Which type of materials are failed by shear?
Ductile.
Very good. All the ductile materials are failed by internally transformed shear stresses. See, in the external surface, whether you are applying the normal load or shear load or combined both normal and shear, it is not a matter. The internally transformed shear stresses are causing failure in the ductile material. Now come to the brittle material. Whether you are applying the normal stress or shear stress or both in the external surface, it is not a matter. Internally transformed normal stresses, it means principal stresses, right, are causing the failure, normal failure. Okay, so all the brittle materials are failed by internally transformed normal stresses. All the ductile materials are failed by internally transformed shear stresses. Okay, right. So first conclusion, the type of failure depends on material. Type of failure depends on material, right? So type of failure means what? What are the types of failure? Shear or normal. Corresponding material type, ductile or brittle. So already you made the conclusion, right? Now tell me, all the ductile materials are failed by. All the ductile materials are failed by. Correct answer. All the ductile materials are failed by.
Shear.
Which type of shear? Where it is calculated?
Maximum internal
Very
shear.
good. Internally transformed maximum shear stress. Excellent answer. Right? So all the ductile materials are failed by internally transformed maximum shear stress. So when this stress, internally transformed shear stress is equal to shear strength, component will fail. Okay, right. Next point. All the brittle materials, brittle materials are failed by tell me answer.
Internally transformed principal stresses.
Very good, excellent, super. Internally transformed normal stress, they are called as principal stress. Very good. Internally transformed maximum normal stress. Internally transformed maximum normal stress, which is called as principal stress. Right. So one more information. Principal stress may be positive or negative. Okay. So in case of 3 dimension, 3 principal stresses will be there. In case of 2 dimension, 2 principal stresses will be there. In case of 1 dimension, only 1 principal stress will be there. Sir, then what about remaining principal stresses? For example, in case of 1D, only 1 principal stress, sigma 1, is available, non-zero value, 100 megapascal. Sigma 1 is 100 megapascal in 1D. What about sigma 2, sir? 0, assumed as 0, because 1D is assumed assumption, right? Sir, sigma 2, 0, sir. Sigma 3, 0, sir. Right. For 1D. Right. Then 2D, sigma 1 is 100 megapascal, sigma 2 is minus 20 megapascal, sigma 3, 0, sir. 0. It is assumption. Right. In case of 3D, sigma 1 is 100 megapascal, sigma 2 is 20 megapascal, sigma 3 is minus 30 megapascal. Okay, right. So what I'm trying to say is principal stresses may be in the positive value or it may be in the negative value also. Okay, right. The maximum value is called as major principal stress. The least value is called as minor principal stress. Okay, right. So here failure is caused by maximum normal stress. Failure is caused by maximum normal stress, right? Actually, it is a Rankine theory. It is a Rankine theory of failure. Okay, right. But you have to know that minor principal stress also available. It is major principal stress. It is major principal stress. Minor principal stress also available. You have to keep this in mind. Right? So, what is a principal stress? Principal stress definition. Principal stress. So already you told, right? Internally transformed, right? So the max extremely possible. Extremely possible. Internally transformed normal stress. Right. So why I am using the word extreme? It because the principal stress may be in the positive or negative. It may be maximum or minimum. So what is a combined term? Combined term. Which term? Which word is representing both maximum and minimum? Tell me. Which word is used to represent both maximum and minimum? Proper word. Extreme. Extreme. That is why I have used the word extreme. So the extremely possible internally transformed normal stress is called as principal stress. Okay. Don't forget, in case of 3D, three principal stresses. In case of 2D, two principal stresses. Third principal stress is assumed as 0. In case of 1D, only one principal stresses. Other two principal stresses are assumed as 0. Okay, right. So now you can understand, right? You are going for industrial visit. You are going for industrial visit, right? I am also your classmate. Right? We are all going to industrial visit. We are seeing that one engineer, right? Structural engineer is calculating the principal stress. Calculating the principal stress. It means he is working on which type of material. He is working on which type of material. Quick. Brittle material, super, excellent. Brittle material, because why he is calculating principal stress? He has to compare this principal stress with the strength, right? So principal stress means what? Internally transformed maximum normal stress or minimum normal stress, right? So he is going to calculate internally transformed maximum normal stress. That should be compared with the normal strength. It means normal stress is compared with the normal strength means it is used for brittle material only, because brittle materials are failed by internally transformed normal stresses. Right? So we are going to next room, design room. In the design room, another structural engineer, structural analyst is calculating tau max. Right? It means he is working on which type of material. He is working on which type of material. Ductile material, excellent, super. Ductile material, right? Are you clear now? This slide is very important slide. Is it clear now? Right. So the type of failure depends upon the material. Okay. Another information is failure occurs due to internally transformed stresses. So in whether the component will be fail or not, right? For that checking, compulsorily you have to do the transformation process, right? Then all the brittle materials are failed by internally transformed normal stresses. They are called as principal stresses. All the ductile materials are failed by internally transformed maximum shear stress, right? They are called as tau max. Okay, right. One more information I told, right? Sometimes without doing the transformation calculation, we can go for theory of failure. That is a special situation. There are 9 types of special situations. Right? Around 9 types of special situations. Right? So we are going to discuss about Moore circle for all the 9 standard cases. Right? They will be asked in the examination. Right? All type of a competitive examination. Right? So the specialty in that case is, right, internal stress is equal to external stress. Internal stress is equal to external stress. So what do you want? Inside the material, you are going to calculate the principal stress. It means at some angle, internal stress, that is principal stress, is equal to externally applied stress, right? At what angle it is possible?
0.
0 degree, right? At 0 degree, internal stress is equal to external stress, right? Don't forget, right? Additional point, right? So our plan is, right? See, already I told you, tau max is calculated by you. Where you are calculating? External surface or inside the material? Tell me. Where you are calculating? Tau max?
Inside.
Inside the material. Very good. Super. Inside the material. So tau max versus shear strength. Shear strength is called as which type of theory of failure? Means it is guessed theory of failure or Tresca theory of failure or tau max theory of failure. Different names. Okay, right. So another specialty is there. Another specialty. It is a safest theory in the world. Safest theory in the world for ductile material. This theory is suitable for ductile material. This theory is suitable for ductile material. Next information, right? So additional information, two things. What I told, right? What is a specialty? Suitable for which material? Ductile material. What is another information I told? Safest theory in the world. Safest theory. Right. Next, sigma 1 versus tensile strength or normal strength, right? Tensile strength or normal strength, right? This theory is called as Rankine theory of failure. Rankine theory of failure. Right. It is suitable for brittle material. Okay, so keep this point in mind. So you have to think that whenever we are calculating the stress, what is the next step? We are going to do the transformation process. Right. Then what is the outcome of transformation process? There are two possible outcomes. One is principal stress, another one is tau max. Right. When we are using the principal stress in the brittle material, when we are using the tau max in the ductile material. Okay, right. So I will give the overall outline of the strength of material now. It's a very important slide. What are, how many stresses are available? How many stresses are available totally?
7.
7 stresses. Super. 7 stress. Sigma T, sigma C, sigma bending, sigma thermal. 4 normal stresses, right? Then tau turn, tau transverse, tau torsion. 3 shear stresses, right? So totally 7 stresses are available. Totally 7 stresses are available, right? From these 7 stresses, we have to frame the stress tensor. We have to frame stress tensor. Right. 3x3 matrix. Stress tensor is nothing but 3x3 matrix. Just arranging the 7 stresses in the form of matrix. That's all. So why we are doing this process? Once you fix these 7 stresses in the matrix format, it is easy for transformation. That is why we are doing. Okay. So don't fear about the stress tensor. I will explain in the easiest way. Right. It is a 3x3 matrix. 3x3 matrix for 3D. It is a symmetric matrix. For 2D, it is 2x2. Okay, right. Okay, sir. Stress tensor is framed, sir. Right. What is the next step? Transformation. Right. Transformation. Note this. Transformation. Right. So before going to transformation process, 7 stresses should be arranged in the form of 3x3 matrix. Right. We have the techniques. We have the techniques to fit the 7 numbers in the 3x3 matrix. Right. Very important step. Right. Next, transformation. Transformation. Now we are entering inside the material. Transformation. Right. What is the graphical name of the graphical method? Mohr circle. Mohr circle. Right. There are 2 methods used for transformation purpose. Right. One is analytical method, formula method. Another one is graphical method, Mohr circle. Right. What is the outcome? What is the outcome? See, very important step here. First, actually, you know, right? Principal stress, tau max. These are the outcomes, right? These are the outcomes. Right. Now, watch here. Sigma 1, sigma 2, sigma 3. Right? Then tau max. Right. So, 2 categories. Say, first category principal stresses, second category tau max. Right. Then, from the principal stress, sigma 1 is used to compare with the normal strength. Means tensile strength. Right. For which material? Brittle material. For brittle material. Okay. Right. For ductile material, tau max is compared with the shear strength. Tau max is compared with the shear strength. Okay. Right. So already you have calculated tau max from the transformation process. Right. There is another way to calculate the tau max. From the principal stress also, we can calculate tau max. Right. So what is the formula? Tau max equal to sigma max minus sigma minimum by 2. Right. Major minus minor principal stress divided by 2. Okay. Right. This is for ductile material. Ductile material. Right. So this is the full outline of strength of material. Right. So what is the name of this process? Stress versus strength comparison. What is the name of that process? Comparing the stress with the strength. What is the name of that process?
Failure.
Theory of failure. Very good, very good. Theory of failure. Right. So now you have seen full strength of material. Right. So hereafter, whatever I teach, you can understand where we are standing. Where we are standing. Right. So our plan is we have to study all the 7 stresses. All the 7 stresses. First step. Right. Then we will study about the tensor, stress at a point, tensor. Right. Then more circle, both analytical method and more circle, both we will study. Then theory of failure. It is our plan. Okay, right. So before starting the 7 stresses, we will start with the strength. We will start with the strength. Only 2 types of strengths are there. Okay, right. We will start with the strength. Right. So we will complete the strength information, very small information. Then we will go for stresses one by one. Okay, right. So yesterday